Welcome to the 24th lecture in general topology. The topics that we will explore in this lecture include a conclusion of our study of the exotic topologies on the reals, that is, the Sorgenfrey line, Michael line, and the K-topology. The final or inductive topology, which is the dual of the initial or projective topology, and an introduction to the quotient topology and quotient spaces. Okay, so recall that the Sorgenfrey line is a disconnected first countable separable T4 space with no isolated points but is not second countable Now, as the Sorgenfrey line is T4, it is normal and Hausdorff. Further, as the Sorgenfrey line is T4, it is also T3 and hence regular. And as the Sorgenfrey line is Hausdorff, it is also T1 or Frichet and T0 or Kolmogorov. So next we'll look at the first exercise from the previous lecture. And we'll show that the Sorgenfrey line is not compact. So proof. As the collection script A of all open intervals from n to n plus 2, where n is an integer, is an open cover of the real line that does not have a finite subcover and the lower limit topology is strictly finer than the standard topology. On the reals, the collection script A is also an open cover of the Sorgenfrey line that does not have a finite subcover and hence the Sorgenfrey line is not compact. So we can now summarize the properties of the Sorgenfrey line. The Sorgenfrey line has 0 isolated points, is not connected, it is disconnected, is not compact and is not second countable. It is first countable, separable, normal, and regular. It is T4, T3, and satisfies all the separation conditions: Hausdorff, Frechet, and Kolmogorov. So recall that the Michael line is a disconnected first countable regular T1 or Frechet space with uncountably many isolated points and is neither second countable nor separable. Now, as the Michael line is T1 or Frechet, it is T0 or Kolmogorov, and as the Michael line is regular and T0 or Kolmogorov, it is Hausdorff, So next we will look at the second exercise from the previous lecture, and we'll show that the Michael line is normal. So proof: let the sets E and F be closed disjoint subsets in the Michael line. Now, as the sets E and F are closed, their complements are open, and as the sets E and F are disjoint, the closed set E is contained in the complement of F, and the closed set F is contained in the complement of E. That is, the complement of F is an open set containing all the points of E, and the complement of E is an open set containing all the points of F. And so for every point E in the set E, there exists a basic open set which we'll call B sub E, such that the point E is in this basic open set, which is contained in the complement of F, and for every point F in the set F, there exists a basic open set, which we'll call B sub F, such that the point F is contained in this element, which is a subset of the complement of E. And so the set U, which is the union over all points in the set E of the basis elements B sub E containing those points where each basic open set B sub E is contained in the complement of F, and the set V, which is the union over all points F in the set F of basic open sets B sub F containing them, where each basic open set B sub F is contained in the complement of E, are open neighborhoods of the closed sets E and F, respectively. Now suppose that there exists some point x in the intersection of U and V. Then the point x is in the set U and is in the set V. So as the point x is in the set U, x is in the basis element B sub E for some point E in the set E, and as the point x is in the set V, the point x is in the basis element B sub F for some point F in the set F. Now if the basis element B sub E is a singleton, the point x is equal to the point E, which is also contained in the basis element B sub F, which is contained in the complement of E, which contradicts the fact that E is a point in the set E. And if the basis element B sub F is a singleton, then the point x is the point F, which is also contained in the basis element, or is an element in the basis element B sub E, which is contained in the complement of F, which contradicts the fact that F is a point in the set F. So we may assume that the basis element B sub E is an open interval with endpoints A and B, and the basis element B sub F is an open interval with endpoints C and D for some real numbers A, B, C, D. Now, as the basis element B sub E contains a point E of the set E, we have that A is strictly less than E, which is strictly less than B. So either the point x is in the half open interval from A to E inclusive of E, or x is in the half open interval from E to B inclusive of E. And As the basis element B sub f is contained in the open interval from C to D, we have that C is less than f, which is less than D. So either the point E is in the half open interval, correction, the point X is in the half open interval from C to F inclusive, or is in the half open interval from F to D inclusive of F. In all cases, the points E and F are contained in the intersection of B sub E and B sub F, the basis elements containing the points E and F. So the point E is in the basis element B sub F, which is contained in the complement of E, and this contradicts the fact that E is in the set E. And hence, by contradiction, the intersection of U and V is empty. And so U and V are open neighborhoods of the closed sets E and F respectively, such that their intersection is disjoint. And thus the Michael line is normal. So since the Michael line is normal and Hausdorff, it is T4, and hence also T3. So next, we will show that the Michael line is not compact, and for the same reason that the Sorgenfrey line is not compact. So proof. As the collection script A of all open intervals from n to n plus 2, where n is an integer, is an open cover of the real line that does not have a finite subcover, and the topology of the Michael line is strictly finer than the standard topology on the reals. The collection script A is also an open cover of the Michael line that does not have a finite subcover, and hence the Michael line is not compact. So now we can summarize the properties of the Michael line. The Michael line has uncountably many isolated points. The Michael line is not connected, it is disconnected. The Michael line is not compact. The Michael line is not second countable. The Michael line is first countable, but is not separable. The Michael line is normal and regular. The Michael line is a T4 space and a T3 space and satisfies the separation conditions. It is Hausdorff, Frechet, and Kolmogorov.